All right, so this is our second unit on physics, and it's our first topic, I guess. I sort of split it into three topics, and the first one here is on heat. It says heat and friction. Friction is a phenomenon that has been well understood for centuries. When two surfaces are rubbed together, the parts that touch resist movement, leading to the generation of heat. This resistance is known as friction. So you probably already knew what friction was, but I guess that's sort of like a scientific definition of it. But yeah, as long as two things are rubbing together, it's going to resist, I guess, movement. And that resistance creates that heat. So heat is that byproduct of friction. And you might think of, whenever I think of friction, I think of people using like two sticks together, rubbing them together to get like a spark to be able to start a fire. I know that seems probably extremely difficult, but people in the past would have done that, and that is an example of friction. So they're rubbing two things together to create that heat, and that heat could eventually, I guess, generate a spark. And that's what people used to use to start fires. It says friction causes a lot of problems for machinery and living systems. However, we need friction for simple tasks like walking or creating fire. So yeah, like what I said, creating fire, but also walking, we need that friction in order to keep us on the ground. I don't know if you've ever tried to walk on ice. Ice would be our, I guess, real life example of basically frictionless surface. So when you step on ice, you can fall really easily. So that friction on a regular floor is going to give us the ability to not fall, right? So friction can be good and bad depending on where it is in our life. It says heat and the Brownian motion. It says although the heat that is generated by friction can be a nuisance, we can also use it for a lot of things. But what exactly is heat? Well, heat can be explained by something called the Brownian motion. And basically this talks about how particles are always moving around and colliding into each other. Heat is simply the consequence of faster particle movement and more frequent collisions. This is particles that have more energy exert more heat. So basically what friction, or the example, and there's a video here, I believe, yep. I will post it on the Google Classroom, but basically the idea here is that when things get heated up, so they get some energy in them, they get warmer. We know that warmer things tend to move, their particles move faster. So when things are moving faster, there's more chance that they're going to crash into each other. And that crashing into each other is, I guess, that the consequence of those faster particles moving around. And that is our sort of the reason why friction and that heat is created. And I will post that video so you can watch that separately. Just can't watch it inside the video. It says heat, kinetic energy, and temperature. It says the energy associated with heat or thermal energy is therefore related to the motion of particles or kinetic energy. So as the kinetic energy of particles increases, they move faster and as a result have more thermal energy. So that's sort of what I just said, is basically the faster the particles are moving, the more thermal energy or heat. That's what this is, heat. Oops. That's a fancy way of just saying heat. So the faster the particles move, the more heat that is created. And that makes sense, hopefully, to you, that maybe if you're cold and at some point someone might say, oh, just like run around a bit or move around. And when you're moving, you're going to create more heat. So that's the same thing with particles, as they move around, they're going to create more heat as well. So the faster they move, the more heat they create. Particles of cold substances have less kinetic energy because they move slower. So the slower you move, the colder you are. So hot substances, those particles tend to move faster. And you might notice that when you're boiling water, I think, or I notice it is if you put a pot of water on the stove, you're not going to really see any movement within it. And then as it gets hotter and hotter, those particles are going to start moving around faster, and that's going to create that boiling, and you're going to see the like bubbles and stuff being created. That's like that byproduct of heat, but also like just sort of a visual of the fact that like as you heat things up, you're going to be able to see that movement in them if they get to that boiling point. All right, so that's the very first topic, topic 1A, I guess. I split it into little sections, and I'm just going to keep moving on to the next one. This is topic 1B, and this is on heat transfer. So there's different types of ways that we can transfer heat. So once we know that heat is created by particles moving faster, now we can look at, well, how can we transfer heat from like cold things to hot things, for instance. So how does that water on your stove get hot when you took it out of the tap and it's cold? Well, heat was transferred to it from the element or the fire or the whatever you have on underneath of your pot on your stove, and that's using one of these methods. So the heat is only transferred from one thing to another. Okay, and there's 3 ways that we can transfer heat: conduction, convection, and radiation. It says heat transfer explains why your hot cup of coffee gets cold so fast. So even me right now, I have a hot cup of coffee. It's actually not getting it. It's already cooling down because the air around it is colder than the coffee, right? So as time goes on, the heat from the coffee is going to escape into the air and basically transfer. So it's something that you honestly can't even really avoid. As far as your coffee, maybe you can put it in a thermos that's going to keep that heat in from escaping. But having a cup of coffee like this, well, it's going to probably get pretty cold fast, which I don't mind because I like iced coffee. So hot coffee, iced coffee, it all works out. So this is a little video on conduction, convection, and radiation, and I will post that as well. But I will explain it right now. So our first one we're going to go over is conduction, and conduction is heat transfer by contact between 2 substances. So contact between a pot of water and an oven burner causes the pot to heat up, which then causes the water to heat up. So conduction, they give you the example in this picture where you put a metal rod into a fire, and even though the part is on your hand is not heated, it's not in the fire, it'll start to heat up, and sort of the heat will transfer up that rod and burn your hand. And you may have done that as well if you had like a metal spatula or spoon or something in a boiling pot of water. So even though the part that you're touching on your hand isn't in the hot water, it's going to start to move up that, and then you could touch the metal part and it could burn you. So conduction is that first one here, and that's literally just transferring when 2 things touch each other. Okay, and that's what we would see typically in our kitchen. Convection, you might have heard of convection ovens. This is where heat transfers through air currents. So convection allows us to heat our homes. Heat from a heat source is distributed through the air or through the room, causing the entire room to heat up. So this is like if we have a heater on the side of our room, the whole room is going to start to get warm, and that's because the heat will travel through the air and through air currents. Convection ovens allow us to cook things evenly by distributing heat throughout the entire oven. So these sort of convection systems, they use hot air basically to evenly distribute the heat throughout. And convection ovens, they tend to, cook things a little bit faster just because they have a good distribution of heat and more evenly as well. So convection is our second one here, and convection is where the heat transfers through the air. So there's no contact. On the last one, there was contact, right? Conduction, you got to touch the hot thing to get the thing that you want to heat up. In this way, convection is just, it's through the air, so we don't have to touch the heat source. We just have to heat up the air around the heat source to heat up what we want. And then the last one is radiation, and you may have heard of this before. Heat transfers through electromagnetic waves. We can warm our hands on a fire because of radiation. Radiation is produced by the vibration of electrons, which vibrate more rapidly when heated. So radiation is actually somewhat of it's a good thing in a lot of ways, but it also can be a bad thing because, UV radiation, which it's talking about here, that's something that could cause us to get like skin cancer. Radiation is used in like cancer treatment, where they will basically heat up the electrons around like a tumor or something to be able to kill it. So radiation could be really strong, but radiant heat is literally just that sort of moving through the air. And it's a lot like convection in a way, but it's actually heating up those particles in the air as opposed to just sort of using the currents of the air to move. Okay. Heat transfers in nature, it says, because particles that are cool tend to be more compact. Cold air is more dense than warm air. This causes cold air to sink while warm air rises. The circular movement of air that results from the rising and sinking of air leads to convection currents. The wind you feel is simply a convection current. Okay, so even having wind is just the byproduct of these convection, the hot and the cold. So those hot and cold pockets of air are sort of going to move around the earth even, and that's how people can predict weather, is because they know how these hot and cold air pockets will sort of move, and they can have a good idea of sort of what the weather's going to be like, just due to like the wind currents and then those hot and cold air pockets. Whoa. This shows you two different pictures, a land breeze and a sea breeze, using those convection currents as well. If I look at the first one, it says at A, the sea loses heat more slowly than the land. The air over the sea is warmer. And then at B, it says warm air over the sea rises, air over the land is cooler, and the cool air is more dense and sinks. And then cool air flows towards the sea to replace the warm air that has risen. So it's sort of like a cycle. We're going from, this hot air is rising, this hot air has risen, but when something that happens with air currents is that when they sort of like hot air and cold air, they want to like meet each other. They want to balance out. So if you have a really hot area and a really cold area, they're going to try that. Those air currents are going to like rush to each other to sort of level out. So when you have a really hot pocket right here and a cold one over here, then this hot air is going to want to move over to sort of heat up that area. And because this cold air is dense, it's heavier, it goes down. And when that goes down, it's down closer towards that warmer pocket again, so it starts to rush towards it, warms up, and the cycle continues. So that's sort of what happens when you're on the coastline. I don't know if you guys have ever been like on the ocean, for instance, but it can be really cold on the ocean, depending on which ocean you're on, but also that land and sea sort of exchange is very helpful for like people who live in BC, for instance, because that warm air from the Pacific Ocean, due to the currents of the ocean, convection currents is what they call them, they basically bring warmer water up the coastline of BC, and then that warm air goes onto the land, heats it up, the cold air gets pushed out. So that's why the climate in BC, or on the coast in like Vancouver Island, it's a lot warmer than it is here, and that's really just due to the fact that that warm air from the ocean is heating up the land. On the other hand, we've got sea breeze. So it says sun rays warm land more rapidly than they warm the water. So this would be like an example of the Pacific Ocean, like BC. And this would be an example of the Atlantic. This is where I'm from. I'm from Nova Scotia. So the sun rays warm land more rapidly than they warm water. Warm air is less dense and warm air rises. So the warm air over the land, it starts to rise up. And that rising air wants to, again, move this way and fill in this, I guess, colder section. Because it'll start to get colder because it's over that cold ocean. It'll start to get dense, go down. That cold air will try and rush over to fill in this warmer pocket, and the cycle will continue. So the big difference here is that on the Pacific Ocean, the water's warmer than the land, and that helps to warm up the land. On the Atlantic Ocean, where I'm from, the land is normally a whole lot warmer than the ocean. So the ocean tends to actually cool the land, and that is, again, not necessarily good, but it's still, I guess, warmer than here. But depending on where you are and depending on the ocean currents, that'll sort of show you, and I don't think it does show you in this PowerPoint, it's beyond this, but those ocean currents, they basically bring either cold or warm air to the coasts, and depending on what part of or I guess what currents are happening around you, that's going to depend on what type of climate you have on that shore. And that cold air, or the cold water that's on the Atlantic, is actually coming from the north. So it makes sense that it's coming down the coastline, and it gets warmed up in the Caribbean, and then actually that warm water moves up into Europe. So that's why the climate in Europe tends to be warmer than, for instance, on the east coast of Canada, just because they get the warm currents in the ocean, where on the east coast of Canada, they get the cold water. Anyway, that's probably too much information. I'll just keep going. I think it's really interesting, sort of the way that the weather changes just because of the way the water moves. So heat transfer in nature, it says because oceans are able to store large amounts of thermal energy, they actually help to moderate the climate of land areas near them. This means that they prevent the area from becoming either too hot or too cold, and here's how it works. In cool weather, an ocean can release a great amount of heat without cooling much itself. Even during very hot or cold days, the temperature of the ocean remains constant. As the sun warms air above the ocean, that flows from the air into the water, cooling the air. When the temperature of the air above the ocean cools, heat flows from the ocean to air and warms the air. So basically, there's a whole lot less air than there is ocean, so it's really easy for the ocean to be able to cool and warm the air, and not really affect the temperature of the ocean. Okay, so that's sort of how the ocean stays pretty constant. I mean, in an area, and that's good for, I guess, plants and animals that live in that water, so that they're not having a huge fluctuation in water temperatures. And then I will do this last topic here, which is topic 1C, and it's heat transfer technologies. So some technologies that we use to get rid of heat. It says, for many technologies, thermal energy must be removed to prevent overheating. Combustion of fuel inside of an engine, for example, produces large amounts of heat. So inside of your car, there's a lot of heat happening. If you didn't have a sort of cooling system, which it just talks about here, it's the liquid coolant, which is pumped through the engine block to the radiator. Through the process of convection, heat from the engine is transferred to the air. So they're basically this cool liquid, or this liquid moves through, gathers the heat, so it touches that radiator, which gives it the heat, and then that heat can be released out of the car so that your car doesn't overheat. And you might see, if you've ever noticed, you might not drive, but if you look at it in your parents' vehicle or someone's vehicle, you'll see that right where you see how fast you're going, that speedometer, there's normally a little, I don't even, what's the word for it, but basically this little gauge that tells you how hot or cold your engine is. And in the winter, I notice on my car when I turn it on, it's as cold as can be, and you gotta wait for it to warm up, for that engine to warm up. But in the summer, for instance, it pretty well stays the same. Like, it doesn't really overheat. So that's that coolant that's working to get the heat out of the engine and into the air around you. So that's, we have coolants, but then we have things that, cool stuff down, but then we also have things that will, I guess AC is what we're talking about here. It says, when you sweat, water produced by sweat glands helps cool your skin through evaporation. Thermal energy is transferred from your skin to the water via conduction. Okay, so sweat is a natural way of us to cool. And you might think, oh my God, I'm sweating and I need to wipe this off. Well, you do need to wipe it off, because that actually in that sweat is where the heat is. So if you take the sweat off, you're going to be removing that heat. And I don't know if you've ever sweat before, and then maybe like 10 minutes later, if you don't really like get that sweat off of you, you might start to feel cold. And that's because that heat is escaped from the sweat, and now you're just sitting sort of like wetness on your skin, and you tend to start to cool down. So your body is using that sweat to cool you down, because it wants you to stay at a certain temperature. The notion of cooling through evaporation is used in refrigerators as well. A fluid coolant circulates through the pipes of the fridge, and heat from the food transfers to the cooler air surrounding it. So using that conduction and convection in a lot of ways helps us to rid, I guess, heat. And that's normally what we're doing when we're trying to cool stuff down, is it's sucking out the heat. So on our body, we're sucking out heat and trying to get it out through sweat. In a fridge, it's got this coolant, so this liquid that traps the heat, so the heat is transferred to that coolant, and then it can be released out. And if you've ever felt the back of your fridge, you're going to feel some warmth, and that's that heat that's being released, I guess, from the food or whatever's inside of it. Okay, so that's our topic 1 here on heat in general, our first part of the physics unit. The second topic in this unit is on, don't exactly remember what it's on, but there is no PowerPoint for it, so there's just an assignment that you need to do, and then I'll do another lesson on your topic 3 and post that on the Google Classroom. All right, let me know if you have any questions, and have a good day.